In this video, I'll be talking about how the binary search works. I've got the code already because I want to spend the time of this video to actually explain how it works instead of typing it down and wasting more time. This algorithm is pretty out there on the internet, so let's get started to how it works. So I've got a function here that takes two arguments. Now, the first argument is the value that we are searching for. That's called target. And the second argument is the array that we are going to be using to search for what we're looking for. So basically the target and the array. So how do we call this function? If we scroll down here, we show examples of how this function is being called, passing in the first argument, which is the value that we are searching for, and the array that we would like to search. Now you want to keep in mind that the array or the list that you're passing has to be a sorted array or a sorted list. That's really important because the binary search is only going to work if you pass it a list that's sorted because it relies on order. So if we look at, for example, what is it returning? It basically returns the index at which it's sitting in that array. So 11 sits at index 0, 12 sits at index 1, 13 sits at index 2, and 14 sits at index 3, 15 sits at index 4, and 16 doesn't exist in the list, so we get none. That's because that target is not found. So if I run the code, we actually get the output exactly as we have in the comments. It's only there in a comment because it's a bigger font than what I've got in the console here. Okay, so let's have a look at how this works. So I'm going to use this Excel sheet to demonstrate what's happening. So what we have is the left variable here points at the first element in the list. So left is 0. We've also got our target 11, the array. I've got the indices just to help us know, easier to see the index of each element. Left is 0, and right is the length of the array, which is 5 minus 1, 4. So that points at the last element sitting at index 4, which is number 15. Then we go into this while loop to keep searching while the search range is valid. So as soon as the left is bigger than the right, it will just return none. And that's what happens when we're searching for number 15. This value gets updated too much until it's bigger than the right and we step out of the while loop. And I'll show you an example of how that works when we are searching for number 16. Okay, now let's start with calculating the middle index, and that is what we'd call mid. Now mid is equal to left plus right and an integer division of 2. Integer division, God, I can't say integer division. It just will get rid of the decimal points. So we've got 0 plus 4 is 4 divided by 2, that's 2. So that's our midpoint, which pretty much sits at points at value 13. Next, we want to check if that value 13 is equal to our target 11. In this case, it's false because 13 is not equal to 11. So now we go to the second part. So either we are going to search the left part of the array or the right part of the array. And that's the idea of the binary search. What it does is, I'm just going to take a sneak peek of our next video. What it does is it will half the search range with each step. Every time, half it into half or two parts. And then each comparison removes half of the remaining elements. So the number of comparisons needed to find or not find the target that grows logarithmically. This is why, in the worst case, this has got a log in complexity. And in the best case, it's got a constant time because it finds it immediately, and only one comparison is needed when the search is found or the target is found. Okay, so back to here. What happens? The target is smaller, so search the left half. Is this true? Yes, 11 is smaller than 13, so we have a new range. It's 11 and 12, but let's see how that happens. Now, the right part is going to be updated. So instead of it pointing at the last element, now we want it to point at this part of the array. So how that happens is it mid minus 1. Now, mid is equal to 2. 2 minus 1 is 1. So the new part of the array that we have split is 11 and 12. Now, how many comparisons so far? 1 out of 2. Because now we're going to go back to this part of the loop. So is left still smaller than right or equal to? Yes, it is. So we go into the loop. Now we update mid again, which is left plus right. So 0 plus 1 divided by 2 is equal to half. But because it's an integer division, we get rid of the half, and that gives us 0. So now the midpoint is 11. So what's going to happen is if whatever value of the whatever element sitting at mid, which is 0, if the value of that is equal to target, so 11 equal to 11, true. So I'll just make that unbold, and this would be the bold. True, so now we return mid, and at that point, mid is 0. And this is why we get 0 here. So that took us 2 comparisons in total. Now let's have a look at other examples. What's similar to 11 is number 14. Because first so if we go to 14, number of comparisons needed is also 2. Because the first comparison gives us mid 13 and then splits the array into this part. And the next comparison finds that mid is equal to 14, which is equal to our target. Now this is takes more comparison. Finding number 12 is a little bit more work, so it's an extra comparison. So it's take 3 comparisons to find number 12. Because what we get is the first comparison, we split the list is halved into 2, and the next comparison is another split, so we find 12. Whereas if we're looking at 14, the first comparison splits the list into 2 and finds mid at 14 and finds it. If we're looking at 11, 2 comparisons only because mid is 11. If we're looking at 15, we need 1 more comparison because mid won't be sitting. So these would be our mid. I'm just going to make them red. These would be this is the first mid, first comparison, second mid, and the second comparison, and third, the mid would be updated to 12 and 15. So this is why when we're searching for 12, it's 3 comparisons. When we're searching for 15, it's also 3 comparisons. If it's something like 16, something that's not in the list, it's also 3 comparisons because on the last part, this locks us outside of the loop. So back to here. To find 15, that's 3 comparisons. To find 12, that's 3 comparisons. To find 11, it's 2 comparisons. To find 14, it's 2 comparisons. To find 13, it's 1 comparison. So let's look at 13, for example. Now the mid is, so left is 0, right is 4, and the mid is 13. Now, as soon as we come to this part, it will be true because 13 is equal to 13. That's when we return mid, which is 2. So the output here would be 2. Also, that took us only 1 comparison. So that's a constant time, and this is the best case. Let's have a look at 15. Now, 15, again, left is 0, right is 4, mid is 2. So that's our mid on the first round. This part is false because 13 is not equal to 15. Now, because 13 is not greater than target, we need to update the left. So this is the part that's going to happen. Now, left is equal to mid plus 1. So 2 plus 1 is 3. So now this is our new range. So let's just put it like that. Sorry. That's our new range. And this is our mid. So number 14 is our mid. So pretty much this part here. Yeah. Next, so that's 1 comparison. 1 out of 2, 1 out of 3. Next, we come back here. Now the mid is going to be updated. Left plus right, which is 3 plus 4. That's 7. Divided by 2, 3.5. We get rid of the half, so it's 3. So that's our mid. Now we are going to check, is 14 equal to 15? False. Then we come back here. Is 13 bigger than 15? False. So we are up to this part. Now we want to update left again, which is equal to mid plus 1, which is 3 plus 1. That's 4. Now we come back here. So that's 2 out of 3 comparisons. We come back here. Is left, because there is an equal to sign, that's true. So we come into the loop. Now mid is updated to left plus right. So 4 plus 4 is equal to 8 divided by 2, that's equal to 4. So now we are left down to only one element, which is the last part of the list. And now we're going to check. So now we are in the third comparison, third round of the loop. Is 15 equal to 15 true? So now we return 4, which is that part. Now let's just suppose that we've done all the work, but we are searching for 16. So let's just keep going. Let's just suppose that we've checked that is 16 equal to 15? No. Then is 15 bigger than 16? No. Suppose that we are searching 16 and we've done all the work that we've done for 15. Then it will come to the else and it will update left to be 5. And then when we come here, it will see that left is bigger than right and it will stop and return none. That's why even in 16 is in the worst case, but it still goes for 3 comparisons. So that's pretty much how the binary search works. Stay tuned for the next video where I'll explain more about its complexity. So I'll see you in the next one.